said, hey, you, let's do some diffie-Q. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some diffie-Qs. In this video, we'll be reviewing the major topics that we covered regarding first-order differential equations. Let's start by classifying first-order ODEs. Even as we say first order, one needs to know what order means. So let's look at some differential equations of differing orders to help us decide when we're looking at a first-order differential equation. Here we have a differential equation that may appear second order because of this square, but in fact, if we concentrate on nothing but the derivatives of the dependent variable y, there is the zeroth derivative, and there's the first derivative. To determine the order of a differential equation, we simply determine which order is highest. The highest order we see is first order, so this is a first-order differential equation. Now let's look at another. This differential equation may appear to be first order because on the left we have a y prime. However, we want to look among all the derivatives and decide which one is the largest. Here's the first derivative, but here is the third derivative. The highest derivative we see is of the third order, so this is a third order differential equation. Now, of course, there can be second order, there can be fourth order, fifth order, and so on, to any finite positive integer order. Next, let's look at a set of properties that relate to different methods we can apply to find solution formulas. There are 5 primary properties that we looked at in order to sort differential equations and decide which solution methods we should apply to them. Let's look at examples of each one. The first is a case of a separable differential equation. We can rewrite it changing prime to Leibniz notation, which is not strictly necessary, but I think it helps identify it a little more easily. And then writing this as 1 over x times cosine of y. That's the format for it to be separable. Next, let's look at a linear differential equation. In fact, let's look at a few. Here we have 3 linear differential equations. They're relatively similar, but we've written them so that we can point out different subproperties of being linear. Let's first rewrite each of them so that they fit the standard linear form. Now that each of these have been written in the standard linear form, we can compare them and decide whether we think they're homogeneous and/or have constant coefficients. In order to have constant coefficients, it must be that the coefficient function in front of each of the derivatives, including the zeroth derivative, must be constants. We see that this is not true for the first equation because of the x, the negative cosine. Either one would cause it to be not constant coefficient. But in the second and third case, we have only constants in front of each of the instances of y and y's derivatives. Thus, these two are constant coefficients. In order for a linear differential equation to be homogeneous, it must be that when it's written in standard linear form like this, on the right-hand side, there is nothing but 0. We see that's only true in the very last case. So the only one of these that is linear homogeneous is in fact the last one. Now let's look at a few examples of nonlinear differential equations. Each of these examples is a nonlinear differential equation. If you try to write it in the standard linear form, it will fail. The reason the first one fails to be linear is because of this y to the third. The reason the second one fails to be linear is if you multiply both sides by 2x plus y, you'll have y prime, or the first derivative, have a coefficient function that involves the dependent variable y. In the last case, it's similar. If you were to divide by dx, you would get dy over dx and then have a coefficient function that contained the dependent variable y. Now, not only are these nonlinear, but they also help us see the other 3 properties. In this first case, if we were to ignore for a moment this y cubed, it would in fact be linear. One way to think about Bernoulli differential equations is that in a way they are almost linear. The only difference between a Bernoulli differential equation and a linear one is that when it's written in something like a standard linear form, one has a y to some power over here. So the left side will be linear, but the right side will have possibly some function of x multiplied by y to a given power, like 2 or a half or what have you. So this first example is Bernoulli. In the second case, we can substitute for each instance of x and y the same variable but multiplied by t. If we do that, it'll end up being that the t's cancel out on the right-hand side. And if that's the case, we know we have a nonlinear homogeneous differential equation. In the last case, we've set it up to imply that it's exact. Now one can check that it's exact by taking the partial derivative with respect to y of 6xy, taking the partial derivative with respect to x of 3x squared minus sine y. And if it's the case that these are the same, which they are, then we have an exact differential equation. We'll look at cases of each of these types of differential equations and solution methods in the upcoming examples. The last property will be the autonomous property. For our first order autonomous differential equations, they'll simply look like this. Notice that outside of taking the derivative with respect to x, this only depends on y. Now before we get to our solution methods, let's look at Picards Theorem, which gives us some information about whether we should even expect a solution to exist and whether we can expect that solution to be unique. So here we have the statement of Picards Theorem. In a previous video, we talked about how there is two parts to this theorem. An antecedent, which is everything between if and then, which I've highlighted here. And then there's a consequent, which is everything after then. If the antecedent is satisfied, then we have the consequent. In general, we say that the theorem will apply if the antecedent in a specific example is satisfied. If the antecedent is not satisfied, that is, if f is not continuous near a particular initial value point, or the partial derivative of f with respect to y either doesn't exist or is not continuous near the given initial value point, if either one of those fails to be true, then we say that Picards Theorem does not apply. Because in general, for a conditional statement, if the antecedent does not hold, we don't necessarily have the consequent. We could, but we can't guarantee it. Let's look at a specific example. So here we have y prime is equal to the square root of x divided by y. And then the initial value point of 0, 1, x being 0 and y being 1. If we want to know whether Picards Theorem applies, we want to check the antecedent conditions and see if they hold in this particular case. The first part of the antecedent says that f should be continuous near this given initial value point. So just to highlight, this initial value point here is exactly the same initial value point that's given in the initial value problem. So we want to ask ourselves, is it possible to look near this point, or in this case this point, and have f be continuous near there? And when we say near, we mean in some region around this point. Looking in the xy plane, we have the point 0, 1, and if we consider any two-dimensional region around this point, we'll find that there will always be some point that's to the left of the green point, such as the point A1, such that A will be less than 0. Now the problem with that is if we substitute in A and 1, A being x and 1 being y, into our function f, which in this case is the square root of x times y, we will get something undefined because we'll be taking the square root of 1 times a strictly negative number, a. And taking the square root of that will not return a real number. Hence, f is not defined even, and it is certainly not continuous. Thus, Picards Theorem does not apply here because we have failed to satisfy one part of the antecedent. And again, it should be noted that near this point is important. The near part, which I'll color now, corresponds to taking a region in the plane around the point x0, y0. So even if it's the case that you're continuous at this given point, you still need to check the points around it or near it. And if you cannot find such a region in the plane where all the points in the region, f is continuous at those points, then f will fail to be continuous near this point. One must do the same thing for the partial of f with respect to y. If either fails, then the antecedent is not satisfied. Now let's look at our first example where we use a method to find a solution formula. Here we have a first-order differential equation, and it is separable. We can write the slope dx dt being equal to the product of a function of x and a function of t. Now keep in mind, we usually work with the dependent variable y, the independent variable x. But in this case, our dependent variable will be x, our independent variable will be t. Now if we write out a few steps of the separation method, we have these equations here. Now let's anti-differentiate. We'll move both of these expressions on either side of this equation to the exponent spot of e. And then we'll perform the standard steps to try to isolate x. It's worth noting here that the original parameter we started with after doing the double anti-differentiation here was an orange c, which eventually we compiled everything together to give us a green c1. Now this is a solution formula, but in order to get the general solution, one needs to also find all the singular solutions. Singular solutions, which will denote x sub s, are those that are just a real number k. To find these, it's relatively straightforward. We substitute into the differential equation k for each instance of x. If we do that, we get this expression here, which of course, taking the derivative of k, a real number, will give us 0. And the only way that we can have this be true, no matter what t is if k itself is equal to 0. This shows that there is one singular solution, x sub s is equal to 0. Combining the solution formula here with our one singular solution gives us the general solution. Now let's look at our next example and next solution method. Here we have a first order differential equation, but it's not written in standard linear form. If possible, it's always good to write a differential equation in standard linear form, even when we get to higher order differential equations. Let's do that now. And now that we've rewritten the differential equation, let's go ahead and find mu. Now that we have our mu, let's multiply every term and every expression in the differential equation by mu. Now let's remind ourselves that the crux of the integrating factor method is the product rule. So let's go ahead and use the product rule now. And at this point, we've turned our original differential equation here into a separable differential equation. Let's use separation of variables to solve this differential equation. Note that after doing separation of variables, we have an integral that we have not computed yet. That's because it's not possible to compute this specific integral. Some integrals you cannot compute, certainly with methods that you've seen, and it may not even be possible with any methods. This is one such integral. Yet, we can still solve for y simply dividing by e to the tangent of x. Now in the cases where you have an integral where it's impossible to find a nice formula for the antiderivative, then you can leave your answer in this form where there is an uncomputed integral. However, if it is possible to find the antiderivative, that is to compute that integral, then you should do so. One final note is that by having this plus c, notice that we have a significant term here. So missing that plus c can cause your solution to be off by quite a bit. Now let's look at our next example. Surprise! We actually have two differential equations here, but both of them will use substitution. The first differential equation is a Bernoulli equation. The second is a nonlinear homogeneous equation. When we talk about homogeneous, it will look different for us when we look at linear differential equations and nonlinear differential equations. But for now, since we're focused on just substitution, we have these two equations. Each will have a different substitution, but the general method will be similar. For the Bernoulli equation, there's a standard choice of substitution. For the nonlinear homogeneous equation, there's also a standard substitution. For the Bernoulli equation, this power here is essential for deciding what our substitution should be. The substitution will be u is equal to y 1 minus, notice the 1 minus is yellow like the rest of the substitution, because that will always be the case. But what changes is what you put here. This 4 is present exactly because there's a 4 here. On the other hand, if you have a nonlinear homogeneous first order differential equation, your substitution should always be simply u is equal to y divided by x. Now, we've chosen to do two problems essentially simultaneously to emphasize the fact that once the proper substitution is made, the process is very similar. In each of these cases, we're going to differentiate u and rearrange until we can make all the substitutions that we need at once. So the u is not always going to be the only thing we substitute, or maybe even what we substitute at all. But in every case of substitution, you'll certainly want to at least differentiate u once. With the Bernoulli equation, what we're trying to do primarily is find y prime in terms of u and potentially u prime. Here we've achieved that. Now let's do some work with the nonlinear homogeneous substitution. Again, we're trying to find y prime. Now the reason you want to try to find y prime, notice, is that eventually you're going to have to substitute in for y prime. So in these two instances, that's what you'll want to look for. Now let's do the substitutions where we're actually substituting the red portion. And notice that we can also at the same time substitute for the nonlinear homogeneous case the yellow portion, which in this case we can say y is x times u and make the following adjustments here. Some algebraic manipulation in each case gives us the following. Now in the case of the Bernoulli substitution, let's substitute the yellow portion. And in the nonlinear homogeneous case, let's do a little more algebraic manipulation. Now what we've done is started in each case with a differential equation in terms of x and y, and ended up with differential equations in terms of x and u. Now our equations to start with were equations that were not linear, so we could not use integrating factor. They were not separable, so we could not use separation of variables. The point of substitution is to try to convert your differential equation from one of these types into either a linear differential equation or a separable differential equation or some other type where you can solve it. In the Bernoulli case, we started with Bernoulli, which is neither linear nor is it separable, and what we've ended up with down here is in fact a linear differential equation. That means we could apply integrating factor. And remember that integrating factor will reduce a differential equation to a separable one. So in some sense, we have this hierarchy where there's a type of differential equation. Once we apply substitution to it, we would like to get ourselves down to linear. Then, from a linear differential equation, we'll use integrating factor to get down to a separable differential equation. And a separable differential equation, we always have a method for. In this first case, we started in particular with Bernoulli. Now we won't finish this equation here because we have looked at an example where we have integrating factor. So one would continue this until they get a solution and back substitute appropriately. In the nonlinear homogeneous case, if we look at what we ended up with, we actually now have a Bernoulli. At this point we would do a second substitution, which would convert it from Bernoulli to linear, and then use an integrating factor technique to go to separable. Now, admittedly, this can get quite tedious, even starting with Bernoulli, doing a substitution to get to linear, and then doing an integrating factor technique to get to separable, and then there's still some work doing separation of variables to actually find the solution. In a case of nonlinear homogeneous, it can be even another step on top of that, where we start out nonlinear homogeneous, convert it to Bernoulli, and so on and so forth. Rest assured that once we move to higher order differential equations, there won't be so many steps of converting from one type, applying a new method, converting to another type, applying a new method, and so on. The methods will be more self-contained. Now let's look at an example of an exact equation. Here we have a first order differential equation, but it's not written in the form where we would like to check it being exact. So here is a first order differential equation. But let's write it in the form where we can check whether it's exact or not. Here we've written it in this form and highlighted with colors what we would have called P and what we would have called Q when looking at exact equations. Now we want to take the partial derivative of this expression with respect to y, that is different variable than is presented here, and then check it against the partial derivative of this with respect to x. If they agree, we have an exact equation. First, we have that the partial of the green expression with respect to y is 2x, and then if we check the second partial, we have again that it's 2x. Now, since these are equal, this equation is exact. Once we have an exact differential equation, there is a particular method to finding a solution. So our goal is going to be to find an equation f of xy is equal to 0, such that if we take its partial derivative with respect to x, we get that. That means if we take the antiderivative with respect to x while fixing y, that will give us some indication of what f looks like. We're saying that the partial of f with respect to x here should be the same as this expression, so we set them equal here. And now antidifferentiate with respect to x alone, and that gives us this equation here. Now notice there's some ambiguity left in f. If we take the partial derivative of this expression with respect to x, we'll get this expression. Now g could be anything as long as it depends on y alone. Now notice if we take the partial derivative of f with respect to y, we'll get the following. And now notice that I've kept f in yellow here because I've taken the partial of this with respect to y, getting this expression. Now g has become g prime because it only depends on y. Now this, the partial of f with respect to y, which is just this here, should match up with this purple expression. Setting them equal, we can see that the x squareds match up, leaving that g prime of y must be y squared plus 1. That means that g is the antiderivative of y squared plus 1. Having taken the antiderivative of y squared plus 1, getting this expression, now we can substitute g here, and it gives us everything we need for f. So here is our equation f on the left-hand side, and we set that equal to 0 on the right-hand side. Now this is an implicit solution only. The reason it's implicit solution only is that we won't be able to solve for the dependent variable explicitly. That is, we won't be able to isolate the dependent variable y. Now it's worth asking at this point, are there singular solutions of the form y of s is equal to k? If you substitute this into the differential equation, what you'll find is the following. And then with some rearrangement we get, and assuming that x is not 0, this shows that as long as x varies, k must vary, so k cannot be fixed. Therefore, there are no singular solutions. Notice we don't need an explicit solution formula here to be able to check whether there are singular solutions. Now let's look at our next example. Here we have a slope field on the left. Notice that there are arrowheads on these. They don't need to be there, since for a slope field we always consider the arrows to be pointing to the right, but it doesn't hurt to have them. And we have a variety of first-order differential equations written in a standard form of y prime equals some function of x and y. What we'd like to do is decide which one of these equations does this slope field match. Alternatively, which equation is this slope field the slope field of? Let's start by writing the null lines each of these equations. Now notice we said null lines. There can be more than one. As we see, we have some cases where there is only one, some cases where there is two, some cases where there is an infinite number. It could also be that it never happens. But from this, we can rule out some of these equations matching with this slope field. Namely, the first one, A, should have null lines on the x and y axes. However, we see that some places have a positive slope where there should be a zero slope, so it can't be A. That's the same case with B. In the case of C, there should be a null line along the line y equals negative x. That means there should be zero slopes along this line, but clearly that's not the case. For example, here there's a positive slope where there should be a zero slope. That means that C does not correspond to this slope field. Looking at E, we see that there is no dependency on y. That means as you change y, the slope should not change. All of the slopes should be the same because again, there's no change in the slope as y changes. However, we notice that the slopes do change. There's a negative slope and there's a positive slope. So that means E cannot be the equation the slope field corresponds to. In a similar vein, if we look at f, we notice that this does not depend on x at all. That means that as x changes, these slopes should not change. If we consider all of the slopes where y is fixed at 2, for instance, the slope should not change as x changes. However, we have a negative slope here, and then we have a positive slope here. Thus, we can't have that this corresponds to the equation f. Checking the null line of D, we see that there should be a null line along the identity curve, y is equal to x. And indeed, it looks like along this line we have zero slopes. Since we've ruled out all of the others, we know that this is the equation for this slope field, but if you weren't sure that it was at least one of these, you could do further investigations with other isoclines. Now let's look at the next example. In this example, we have an equation for which we could plot a slope field, and it's a particularly nice type of equation, namely it's an autonomous equation. We notice that if we were to put it into prime form, we would have no instance that we saw of the independent variable. This means that it's an autonomous differential equation, which means that as x changes, there should be no change in the slope. In this case, we can collapse the x-axis and draw what's called a phase diagram. To do that, let's find out when this slope would be 0. Since it's already factored, it's easy to see that we have a 0 slope when y is equal to -1 and -2. Again, we can think of a regular slope field being collapsed in the horizontal sense down to a single axis. Only the y-axis matters. Now we just saw that the slope was 0 when y is -1 and -2, so we'll plot 0 slopes there. Now we want to decide where the slopes are positive and negative in each of the intervals carved out by -1 and -2. That is the interval where y is greater than -1, where y is between -1 and -2, and when y is strictly less than -2. First, let's do where y is strictly greater than -1. Using a test value of y is equal to 0, because y equals 0 is strictly greater than -1, we compute dy dx, and we find that it's equal to 2, which is greater than 0. Therefore, the slope there is positive. All we care about is where it's going to be positive. We know that once we're above -1 strictly, since there's no other place where the slope is 0, after this, they're all going to be positive. Now, the magnitudes will change. Sometimes they will be more or less positive, but they'll always be positive. We draw a positive slope just to indicate this. Now let's do a test value for strictly between -1 and -2. We use the value -3/2 or -1.5 and find out that the slope dy dx will be negative. Now we look at the last interval where y is strictly less than -2. Now if we put arrows on our axis, we would have our proper phase diagram. The last thing that we would do is decide for each of our equilibrium points whether they're stable or unstable. The equilibria occur when the slope is equal to 0. That occurs at the red points. To decide whether they're stable, unstable, or semi-stable, we simply look at whether the slopes above and below them are increasing or decreasing. That shows whether a solution curve is being pulled in closer to the equilibrium or being pushed away from the equilibrium. In the first case, we have that above and below, the arrows are moving away from the equilibria. That would indicate this is unstable. In the lower case, we have both of the arrows moving towards the equilibrium. This would mean we have a stable equilibrium. If it were that we had, let's say, increasing on both sides, that would be an instance of a semi-stable equilibrium, or vice versa if we had both decreasing. Now let's suppose we actually extended this phase diagram out so that it was a more full slope field, and then we graphed solutions in this slope field. So here we've extended the slope field back out. Essentially, we've uncollapsed or blown up the x-axis. Before, we essentially didn't have it, and we had the phase diagram, but now, with it included back, we have what we're used to seeing with the slope field. Now it should be that each of the slopes in a single horizontal level should be all the same. Because I've drawn this by hand, they won't be perfect, but hopefully it looks close enough. Any solution that starts above y equals -1 will look something like this. It'll start here and then just move away from this line y equals -1. If it starts exactly at y equals -1, it'll travel perfectly along. If it starts somewhere between -1 and -2, it will go down for a bit and then asymptotically approach. If it starts at -2, again, it'll exactly go horizontally over. And finally, if it starts strictly below -2, it will go up and asymptotically approach again. These are what are called the typical solutions. Now let's look at our final example. For our last example, we'll look at a numerical method, which is a means of approximating a solution. Previously, we found solution formulas exactly, so we could decide exactly what a solution value would be at a given point. Here we'll approximate these values. Oftentimes there is no nice way, either known or in existence, of finding a nice solution formula to a differential equation, so numerical methods are often all a mathematician or scientist has to work with. Let's see Euler's method in action. Suppose that what we want to approximate is y of 2, and we'll use a step side of 1/2. That means as we go from x equals 1 towards x equals 2, we'll take steps of 1/2. That means we'll do 2 steps, or 2 iterations of the Euler's method process. Without going through the computations in gory detail, suffice to say that our x values are obtained simply by adding 1/2 each time. We start at x equals 1 because that's the one up here. We add 1/2 because that's our step size, going from 1 to 3/2 to 4/2 or 2. And then our y is obtained in a similar way, where we start at a y of 2. To get the next y, we go from the last one, 2. We add to it some value to get the new one. The value we add is not just the step, but rather the step times a computed slope. So at each level here, we compute a slope, where this 2 is found by taking this formula, x times y, and multiplying the values 1 times 2. We take the step times the slope, 1/2 times 2, to give us 2 plus 1, which is 3. And our new point is going to be 3/2 for x and 3 for y. Computing the slope again and going through this process again will give us the new y value of 21/4. Graphically, this looks like this. Where we started at the point 1, 2, we followed the slope of 2 up to we got to the point 3/2, 3. Then we followed the slope 9/2, because that was from this step here, up to the point 2 and 21/4. The approximate value of y of 2 is this y value that we reached here, because x is 2 and we approximated y to be 21/4. Well, that does it for this video. I hope you found this review useful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.